Thank you all for joining the fourth Wind Empowerment webinar that completes the first series. We'll be hosting another series after the Athens conference that will be held on November 3rd through the 7th. The webinar will be, as mentioned before, an hour long with a 15-minute question and answer session at the end. We can have an additional 30 minutes for those that want to stay in for additional questions. We will be uploading the presentations to the website soon, and I'll be sending that link around too. We're hoping to get that before the Athens conference. If you would like to be a presenter for our webinars in the future, feel free to email me at jessica@winday.org. That's kind of confusing. So our presenter for today is Matt Little, and he's a freelance electronic and electrical engineer who specializes in renewable energy systems, particularly focusing on standalone systems for remote electrification. Thank you, Matt. Take it over.
Thanks, Jessica. Hi there. I'm going to be talking for some amount of time. I've not actually been through this presentation before, so I don't know quite how long it'll take, but on some work I've been doing with others on open source wind resource monitoring. My email is there if anyone has any questions now or in the future. I also keep a relatively active blog at www.re-innovation.co.uk. Great, yeah, so hopefully this will cover a lot of the work that I've been doing recently and explain the reasons why I'm doing it. So, just a bit of background for me. If anyone has any questions, if you could either type them into the message window or wait until the end and we can have a bit of a discussion about everything, that would be good. But just type them into the message window as you do it. There we go. So, bit of background. My name is Matthew Little. I've been working in renewable energy systems as an electronic and electrical engineer 14 years now. I had been doing a PhD research on standalone power supply systems. These were very high-tech systems using lots of electronic converters. We had a hydrogen-based storage system, so we converted excess energy into hydrogen and stored it and then put it back through a fuel cell. All very high-tech, very expensive, interesting, but I got back to the point that I'd actually been working on this system for 4 or 5 years, and I'd realised I'd never really lived without electricity for any length of time, maybe one night, something like that. So I decided to look for some placements or do some work on more remote electrification projects, which is what I'm most interested in. And I found this organisation, Engineers Without Borders UK. Some of you here probably have heard about them. There is a number of Engineers Without Borders groups in a number of countries. The one in the UK is mainly a student organisation, and they fund volunteers to go on placements between 3 months and up to about 1 year. And I was chosen to do a placement in the Philippines with an organisation called SIBAT, Sibol ng Agham at Teknolohiya, the wellspring of science and technology. And I ended up working with a Filipino NGO, SIBAT, on various electrification projects, remote rural electrification projects, mainly on their small wind turbine design, but also on some solar photovoltaic pumping systems, which this picture here is, and also on some micro hydro systems. So I was involved with helping to install some of the Hugh Pigott design wind turbines, and I think Hugh is on this webinar. So this is a 1 kilowatt version of his generator, his turbine. This was locally produced, so we were trying to get things built with local skills and knowledge. Mainly the majority of the technology was made in urban centres, so we were based in Manila, so we had a small workshop where we could get fabrication made, and we would take all the parts to site, but we were also trying to train up community members to be able to maintain and repair those systems. So this was a 1 kilowatt wind turbine which went along with 400 watts of solar photovoltaics, and it was used for a water pumping system on an island in Buli, which is it's not so far from Manila, but it's off. You have to catch 2 boats to get to it. It's a very remote island. About 400 people living on the island. This was one of 3 communities. Some people had to walk up to about 2 kilometers to collect water. So this was to power water pumping system. You can see here there is actually an anemometer here, so it's, might suggest a little bit more about the presentation. So as I mentioned, we trained up people to be able to maintain and build these systems themselves. Generally locally, help produce documentation and also hands-on training for a number of local technicians to be able to repair and maintain things. But also we had documentation and training for higher level engineers within the NGO organisation to be able to maintain these systems. So that was a bit of a background to the work that I did for a year. That was in end of 2007 and through 2008. And there are a number of issues with these small wind turbine projects. I'm not going to go into some of the other issues that might have happened on the thing with social issues, and there's lots of other things, funding issues, but here I'm going to talk mainly about some of the problems relating specifically to small wind turbines in remote locations. So, oh, it keeps on flicking forwards, that's a bit annoying. Anyway, so there were some problems with these wind turbines, including the incorrect siting of wind turbines. So potentially they were not put in the windiest position, or they were put in a position where a tree was growing up nearby, or they were put in a place where the wind was turbulent. It was very difficult to find accurate local wind speed data. There was not a lot of meteorological data, even though the Philippines has been very well mapped by the US military, who have had a number of military bases there for a number of years. Some of the proposed sites actually turned out to have very low wind speeds and hence very low resource. Another issue was the fact that there were times of very high wind speed, and if there was no warning of this, then some of the turbines could get damaged, including the one you saw just 2 slides before. Unfortunately, that was hit by a typhoon and has been damaged. I'm unsure whether it's been repaired fully yet. So one of the issues was the high cost of doing wind resource monitoring, sometimes outweighing, or not outweighing, but very close to the cost of installation. Therefore, it just wasn't worth doing. So I wanted to look, as part of the work I've been doing over the last few years, at resource monitoring. And I wanted to look at very low cost, so that you could install this kind of stuff without, for very small even for very small systems, so 500 watts, 1 kilowatt systems. I wanted them to be very simple to use. They needed to be standalone, so you could take them to a remote area and just leave them there and they could record data. I wanted the software to be upgradable or changeable, so if people had different things they wanted to monitor, they could change the software as they needed. I'm very interested in people having a local manufacturer and being able to maintain and fix things locally and also build things locally. I like to know exactly what's going on in the things that I use, and I think that's quite a useful skill, a useful part of a project. And this all ties in with open source hardware, which is what I'm kind of using for this project. So the Wind logger that I've halfway through developing, I suppose, we've got is part of a bigger project that I'm looking to push forwards, and would appreciate people being involved with and helping and have ideas on. And it's basically a renewable energy resource monitoring system, something that you could put down in a remote location and it will measure wind speeds, solar irradiation, maybe water flow at a hydro site, and log it locally. So in the end, I would like all of these boxes within this diagram here to be kind of filled, and I want it to be quite plug and play, but also if people want to get into the depths of it, they know all the code, they know all the hardware, they know all the design, so they can build it themselves or fix things themselves. So here we have a number of inputs. We've got an anemometer to measure the wind speed, wind vane to measure the wind direction. Temperature sensing is sometimes useful, maybe for solar and thermal systems, maybe for biogas installations. Solar insolation, so irradiance for solar photovoltaic systems. Water flow monitoring, that was a little bit of a special case for this data logger has been used to monitor the flushing of latrines in a project in Uganda. We developed a small sensor which senses when water has gone past it, and that was like a flush of latrine. And also water flow rate, so some kind of sensor which you can plonk into a river and it will record the river flow rate. So then that will all be stored within a central data logging system, and that will record data to some kind of memory, which can be analysed later on a computer system. Or that data could be sent via a text message or some kind of mobile data logging system, or through Ethernet to the internet, or an add-on screen so you can see the data, or connect to a Wi-Fi network, which may be locally, or you could add this to some kind of wireless connection to some kind of receiver that's a bit further away. I also wanted to look at having this remote, so looking at solar photovoltaic supply for to power and recharge the unit, but that's again slightly optional, and I'll go through what we actually ended up doing in a bit. So probably a lot of you know about wind speed measurements and why they're needed. Obviously the energy output from a wind turbine depends upon the wind speed resource, the wind resource that's available. We need to know that speed relatively accurately to give us confidence that it's sensible and economic to install a wind turbine in that particular location. So, wind farms, they obviously a huge investment into those things. It's worthwhile then putting a few $1,000s into putting a very robust and reliable data monitoring system installed for 6 months to a year in the location. That is worthwhile them doing, and it's a cost that they can justify. With the smaller installations, we may be talking 500 watt wind turbine, 1 kilowatt wind turbine. Then those costs, a cost of maybe $1,000 or $2,000 just to put in a monitoring system for 6 months is too high, and obviously won't be done. So generally we just rely upon a basic site assessment, maybe talk to local people, maybe take a few readings. If you can correlate it with any wind maps available, you could do that. You also look at the local topology and see where there might be a sensible place to install a turbine. Requires a bit of knowledge, past knowledge of installing turbines. So this is a typical wind speed distribution, and we can see what we do is we are putting the wind speeds, the different wind speeds, into bins, and we're looking at the probability of that wind speed happening in a particular area. And this is it keeps on doing that. This is a variable distribution that generally follows a curve like that. And we've got a few points that are interesting to note. We need to know that there is going to be enough wind in this kind of middle area to justify installing a wind turbine. Beneath a kind of cut-in width speed of a wind turbine, we don't actually collect any of that wind energy, and above a cut-off or a rate, cut-out wind speed, we don't actually collect any of that. So we need to know that the wind speed and the probability of a wind speed is within the range of the wind turbine, and that it's sensible for us to actually install a wind turbine in that location. We sometimes draw this information as what's called a wind rose, and this shows us the wind speed in sections around with a direction. So we can see on this particular diagram, vast majority of the wind is coming in from the north to the west. There's not much wind from the south to the east. So having a look at the local topology to be able to figure out either why that is, or installing our system so that it is good for collecting that wind makes a lot of sense. So in order to measure wind speed, there are a number of sensors we can use. The most common is the cup anemometer. This is, you will have seen one of these around, I think. It's a number of generally 3 small cups on a rotating wheel. And it rotates at a rate proportional to the wind speed. They're widely available from very low-cost units to very high, very well-calibrated units. Price range of the one that I've been using is about £2.50. It's about $4, and I've used well-calibrated ones which cost in excess of £400 each. Generally they have a frequency or a pulse output which relates to the wind speed. So we get an output frequency, and that frequency is proportional to the wind speed. And we need to know that characteristic between the output frequency and the actual wind speed. So they generally need to be tested and calibrated. There's another type of anemometer we can use, which I'm just mentioning here really. This is called the ultrasonic anemometer, and it has a number of sensors around the top here. They send out and receive ultrasonic pulses, and the difference in time between those pulses arriving will depend upon the wind speed and the wind direction. These are pretty interesting. There's no moving parts, and they also measure wind direction at the same time. But I've discounted these at the moment because they're just a bit too high-tech. They need too many expensive components. They also need to be powered all the time, and a pretty high cost at the moment. Potentially, this could be included in the future. So there's lots of anemometers available. I've just given some examples here. Vector Instruments and Energy Systems make high quality kind of calibrated units. InSpeed Vortex and Logic Energy, I think they use the same anemometer. I think it's been bespoke designed for them. And that's slightly cheaper, but all good options. The anemometer that I chose for this particular project, and I know there are issues with this, I'm not saying this is the best anemometer, it is a very cheap anemometer, and it is from Maplins in the UK. It is designed to work with small low-cost weather stations. It has a pulse output, so it has a small magnet which rotates inside, and that has a reed switch which gives a pulse output. But I know that it's not very robust. I wouldn't be surprised if some of these fail in use, and certainly in high wind speeds. And also the output frequency to wind speed is not accurately known for these sensors. I couldn't get any information from Maplin, but I have got some information from some testing, but I'd like to do some more testing in a wind tunnel. So generally we want to log the data, we want to log the frequency of the anemometer, and we then analyze it later. In a typical situation we would be recording this data often, so looking at the frequency every second, and then we would generally average it, and the 10-minute average is the useful one for wind speed measurements. And then we can store that data along with a time and a date stamp. And that's exactly what this this unit that I've developed does. So the first thing to do is look at people who make them already, and there are a lot of people that make data loggers already. And a couple of examples here, which are both very good units. The InSpeed Vortex is very clever. It uses a bicycle computer, so genius idea, to record the average wind speed. So the pulses from the anemometer go into the bicycle computer. That, along with a calibration factor, means that the average speed of the bicycle, or the anemometer in this case, relates to the average wind speed in that location. This doesn't give us much detail, so we can't do the probability density of the probability function for this, but it does give us an average wind speed, and it's low cost, very clever use of parts. And Logic Energy, based up in Scotland, produce a nice range of low-cost data loggers for wind resource assessment, and they're good and low cost, and I'd say have a look at their range of things. I think nothing that was out there directly fitted with the objectives that I'd put forward, mainly to do with the fact that it was open source and fully configurable, so that we could upgrade the software as needed. We can repair it. We can take out components. We know what every wire in there does. That's what I wanted. Also, I wanted a lower cost, but with the detail of the data. So we could do a probability function of the wind speed. So let's go ahead and show what I did to kind of build our own. Firstly, I based this on the Arduino, which is an open source environment for programming microcontrollers. Microcontrollers are small computers, so they have a little bit of memory. You can put a little bit of software on them, and they also have a little clock in them, so they follow instructions like you do in a computer. But they're very low cost, and they don't have any bells and whistles like you get on a laptop or something. The Arduino unit itself, if you were to buy one from Arduino themselves, who produce them, it's £20. There are other copies. It's open source project, so people are allowed to make their own. and they're available cheaper. You can buy just the integrated circuit, the little microcontroller, which is an 18 Mega 328, for about £5. The best thing about Arduino is that it's a huge user base, and it has lots of libraries available to do lots of different functions, and there's a huge pool of shared knowledge, which is great to tap into. There is a picture of the Arduino Uno. It's a small circuit board, and you can see here there are plug sockets to add on what are called shields, which plug onto the top for additional functionality. It's programmed through a USB connection from a laptop or a computer, and that is actually converted with a USB to serial converter, and the small IC here is the one that's the 18 Mega 328. The software is free to download. It's open source. It's pretty user-friendly. There's loads of examples. It's a C-based language, C++ based language. Some parts of that don't work, but it's got a huge user base, and there's loads of libraries and examples to do pretty much anything you'd want. Now, the Arduino has 13 input and output pins, and it has 6 analog input pins. Now, we mentioned before that we wanted to record a timestamp to this data. We also want to record the data onto some kind of memory. We need to read an anemometer input, and we also maybe in the future want to look at reading in a wind vane. So I'm going to go through those various components and how I approached that. The timestamp was provided by what's called a real-time clock. This is a small electronic integrated circuit. I use the PCF6593, catchy name. There's loads of different versions available. There's lots of different real-time clocks available. Just so happened to be the one I had. And this is a little unit which, once you've set it up with a small battery backup, and it knows the time. You can ask it what the time is, and it will say it is now 12:37 on the 5th of August 2014. It's got relatively good accuracy as long as it's been calibrated, it's been adjusted. So that's what I used to do the timestamp. Data was recorded onto an SD card. So we wanted low-cost, readily available data storage. So I decided to use a standard SD card. There's lots of them coming out of digital cameras. There's lots of them available. You can't just directly interface an SD card with one of these microcontrollers, because the SD card only needs 3.3 volts. So you need what's called a level converter, and you also need a library of control functions to be able to write data to an SD card. But luckily someone had already done that work, so I used the Arduino library to do this. There are some problems with putting data into an SD card and getting it out again. So you can't write every second. If you wrote every second data to the SD card, you'd very quickly wear out the memory. There's about 100,000 read-write cycles on every location with an SD card. But you can use a larger card, and I was using 2 GB cards, and I've had, with 1 minute average data, I've had no particular issues over the 6 months I've been using these. And a 2 GB card should be able to store about 4 to 5 years data. The data is stored in CSV, comma separated variable file, and I've written this so that it's human readable. When you see the CSV file, you should be able to understand a bit about the data there. So if we look at the various headings, we've got a reference. That's just something that can be set on the unit. In case you've got 10 units, you want to make sure that the data has come from one or not the other. You've got the date, you've got the time, and in this case there's a 10-minute averaging. We've got pulses from 2 different anemometers. in this case showing 0. We've got a direction from a wind vane which is in 8 different directions. I've included a thermistor to measure temperature. You don't really need it, but I decided to. So it was about 20 degrees. And I'm also measuring battery voltage. Now this is used in case the batteries have run down. You can see that the data is then not valid after the batteries have run down below about 3 volts. So the SD card and the real-time clock, I'd already had a project to build a small data logging unit. So I'd built this thing called the Dataduino, based on the Arduino, so it's got a Arduino IC in there at ATmega328, which can be programmed through the Arduino IDE, but it had already included the SD card unit and a real-time clock. So I've used this as the basis for the WindLogger system. The Dataduino, after you've used inputs for the SD card, has 6 digital input outputs left and 4 analog inputs. All the others are used by the SD card and the real-time clock. The Dataduino doesn't have a USB to serial converter, which is how you upload the code to the unit. This keeps the costs quite a lot lower, but it does mean that if you're going to reprogram it, you will need one of these cables. They're easily available. They're about 10 or 15 pounds, and you only need one for many units. I also designed a small shield which plugs into the Dataduino, which has terminal blocks for the inputs for the battery. It's got some on-off switches and a calibrate switch, and also got inputs for the wind anemometers and the wind vane. So this has been developed mainly as a prototype. I think I've made 20 of these. There's things I'd change, and we'll talk about that in a bit. I've built I've built one main unit which I've had installed in my garden in Nottingham for 6-7 months. But the number of units also went to a number of locations to be tested, and this is the stage I'm mainly at the moment. We also wanted to include a wind vane so that we know what direction the wind is coming from, and I chose a similar unit from Maplin because used for these small weather stations, again it was very cheap. You could use anything you wanted, but the output from this one is an analog signal, and it turns the wind direction to eight different directions. One thing that was quite difficult with this was writing the Arduino code so that it uses very low power. I wanted it to be able to be installed, this unit, in the middle of in a remote location, in the middle of nowhere, and that with 3 batteries, in this case D cells, the big D cells, they should last about 6 months. I'd like to review that and make it last even longer, but this is where I'm at the moment. I've also looked at using a solar PV module and calculated that about a 1 watt solar module will provide enough energy for these units to be used pretty much anywhere. I designed it for the UK in winter, and a 1 watt module will be okay for that. So the thing shown here is a solar panel with a lithium-ion battery, but that's a work in progress. So here is my experimental setup. So I have my anemometer in a very, very, very bad location for a wind turbine, and that's been monitoring data for quite a while. I've also worked on some open source designs for holding the anemometer and wind vane that could be easily bolted together. So this design here has the anemometer, it has the wind vane, it also has a spirit level for leveling the device, and it also is the plane of this holder is meant to run east-west, so that means that you can get it all set up quite easily. And these holes here are for cable tying it or fixing it in some way to a post. Obviously, you want it really at a height that is similar to the wind turbine, or at least know the height at which you've installed it. So yeah, I've had one of these units set up and testing and recording wind speed data since February 2014. It seems batteries are still okay and it's still taking data. I've not properly analysed that data. That's on my list of things to do. John Sumanik Leary took 5 systems to on his trip to South America in September and October this year. He's just returned to the UK, and some of these were built as part of a workshop with a technical school. Some feedback has been given on the actual units, but generally I think they worked quite well, and they were easy to set up. But we're awaiting feedback from long-term use of these units. In his locations, he was installing 2 anemometers, so that in case one is broken by speeds, then there's not much of an issue with that. We've still got another to give you data, hence why there's 2 wind inputs. Other people, including Tom Dixon, who I think is on this webinar, have taken this unit and they've added power monitoring systems, so they're monitoring the current and the voltage from the wind turbine, and using the Open Energy Monitor project, they've uploaded data via Raspberry Pi along with an internet connection, so you can view the data online, which is a great add-on. I'm awaiting the write-up of that. So with this project, there's quite a lot still to do. I've kind of given you a broad outline of what I set out to do and where I'm at, and basically there's a number of things here to do. So the anemometer needs much more accurate calibration. I'd like to test a number of them in a wind tunnel. This has been done by the people at Logic Energy, and they have been very kind to give us their test results and an approximate calibration factor, but they found that there was variation between units, so I would like to get some more data on this. The Arduino code needs to be improved so that it's much more understandable for other people. It's understandable in my head, but that doesn't mean that anyone else can understand it. So I'm trying to write that out, put that into libraries at the moment. Also trying to write a program which takes the SD card data, and you can run that and it will draw you the wind speed density function probability and also a wind rose. That's halfway through. I wanted that to be system independent, so I'm writing that in a particular code. I also need to install a number of these and test them in as many locations as I possibly can under different environmental conditions. I also would like feedback on how usable the system is. So if we were to look at the overview that I wrote, we can see that we've achieved some of these sections to varying levels. I can't say that they're all finished. I'd like to redesign the data logger PCB. I'd like to look at the solar power supply a bit more. There are still a number of parts to work on. So looking at better data logging options, it would be nice if you could log on to a USB drive. It should be relatively simple. I want to finish off the solar photovoltaic design, and also looking at much more at online data options, so sending data as text messages. Also having a local display would be good, but it would require more power, so I haven't really done a local display. I'm very interested in producing an open source anemometer and wind vane. The unit you see here, which is in green plastic, that was printed on a 3D printer, printed for me. And you can see that you can actually get quite a useful thing from these from the 3D printer now. It needs a lot of tweaking. I'm not saying this is a good robust, reliable design, but it's interesting if people can, if say one of the cups breaks and you can just make your own, that would be brilliant. So I'm definitely looking at making a DIY anemometer. There are some other designs out there. I'm also looking at doing lots more real-world testing, and I'm interested in people who are wanting to take these systems and use them somewhere and give me feedback. At present, the cost to build one is about £50. That includes a box and a waterproof box, and it's a DIY kit. The Dataduino itself costs about £25, include parts. That's built in 1s and 2s, so hopefully get that cost down a bit more if I'm making more of them. I'd love people to take the ideas and build their own, take parts of this and build their own, and any feedback's very useful. I've tried to keep quite a good write-up of the project, and that it was on a big web address, so I've put it in a tiny URL there. Hopefully you can get to that one. That's specifically on the Wind data logger. There's more progress on the system as a whole, which includes monitoring irradiance levels and also other types of renewable energy resource. And the details will be put on my blog at reinnovation.co.uk. Yeah, thanks for your time. Hopefully that's been interesting to you. If anyone wants to get involved, please feel free to contact me. There are my contact details, and yeah, I'd love to hear from you. That is the end of my presentation. So I'm not sure. Okay, we'll actually timed that quite well. Wow.
Yeah.
So okay.
Any questions out there?
Can you hear me?
Yep.
This is Tom Dixon. Did you ever get to doing averaging of wind direction in code?
Yes, I did. So, hi Tom, sorry. This problem was that I'm measuring the data every second, and writing the data every 10 minutes. Now, if you just take the wind direction every 10 minutes, then obviously you don't get a very good value from that. So what I've done is I am reading the wind direction in every second, and depending upon the direction it's coming from, I put it into one of 8 bins. So I have 8 different directions, and every second I increment the direction that the wind was coming from, and then I choose the one that was most probable, the one that was throughout that 10-minute period, the one that had the most time that the direction was in. I don't know if that's totally correct way of doing it, but it's a way of doing it. Might need a bit more work on that, but yeah. So I've done some averaging, but whether it's the best way, I don't know. I need to write that up as well, actually.
Makes sense. Yeah.
Okay, cool. Are there any other questions at all?
Hello, good morning. Hello.
Hi. Hello.
Yeah, my name is Rafael from Argentina. I've been a bit involved with the work of John Sumanik, and he showed me your systems in these Dataduino systems.
Okay.
When he was in Chile and Argentina. There's one small question or observation. The way to remove the SD card in your the little cabinet um, are you aiming to make a slot to take it out, or is it supposed to be completely disassembled to take out the SD card? It just it was a bit more. It was a bit complicated.
Yes, John has fed that back to me, and
Oh, okay, okay.
yes, I know exactly what you mean. And in fact, this morning I was trying to take the SD card out of my prototype here, and I was getting annoyed with it. The plan was that the whole board would be much easier to remove, and so easier to get the SD card out. In the end, on the timescale that I had to get the boxes were just a standard size, and they had to fit the batteries in a standard way. So I need to look at that. Definitely, it shouldn't be that it's so difficult to remove the SD cards. On the ones that John has, they are all designed that you take the 2 screws out and you take the whole thing out with a board, and then you can take the SD card out. It was designed that the battery comes out and then the 2 screws come out. But I appreciate what you're saying, and yeah, it's definitely something that I'm looking at to improve it.
Okay, okay. That's just a small observation. That's all.
Yeah, no. It's good. Thanks.
Hi, Matt. This is Esteban from Argentina as well. I've been working with John too in different areas of the country, installing. Actually, we've been installing one of your data loggers in the south, in the Patagonia.
Ah, okay.
And I'm really interested in learning a little bit more about this. So it was really an interesting presentation. And I was wondering if you have ever worked with encoders to measure. I'm trying to measure the furling angle and the yaw angle of the wind turbine of the tower. So I was wondering if you have ever tried or have any information about encoders to measure that angle.
I've used encoders to measure rotation of things actually in a project that moved a solar panel, and I've also used encoders to control just forwards and backwards. I've never done it to measure the yaw angle of the wind turbine, but I think it's a good idea. An optical encoder would be a good way of doing this. The only problem might be that the power consumption or energy consumption of having little LED encoders on all the time might not mean it's suitable for remote locations, but if you've got a power supply, it will be totally fine. If you want to look up Gray's encoding, I think it's called Gray's encoding, which is a way of encoding data, so there's a little bit of error checking in it. And you probably
Sorry,
have
how do you spell that?
G-R-A-Y-S.
Okay.
I maybe if you give me your email, I can send you a bit more information. I think that's probably best because I can't remember some details, but
Right.
I can send you some links to things that might help you. Do you know what resolution you need to get? What are the angles that you're looking at?
I don't think that's an issue really. So
Okay, it's just,
I imagine there's probably a very high difference or big difference between prices for higher or low resolution. So I'd go for something in between. But it's not.
yeah, sure. I mean, this unit should definitely be able to measure that kind of data. There is still some digital inputs and outputs, so you should be able to add that on. I haven't thought too much about it, so I'd have to have a little bit of a think. But if you just send me your email address, then I'll write a bit more information to you.
All right. Thank you a lot. Yeah. I'll send it
Okay,
in.
no worries.
You can use a potentiometer for measuring tail angle similarly to using a wind vane potentiometer. You can even put a wind vane on the turbine, although it's difficult to position it so that it gets the true wind.
Yeah, that's true.
How,
You get a potentiometer that doesn't have an end stop. Is that what you'd mean? Or does it?
You can use a wind vane is normally just a potentiometer anyway, where north is the 0. But if you have a tail angle sensor, for example, that's only going to need to measure about 90, 100 degrees. You can use something like a bit of flexible plastic pipe as a drive, taking it up into a sealed, a weatherproof container, a box that the potentiometer's in. And that makes it quite a simple low-tech method of measuring the angle of the tail. There are obviously 3 things to measure. There's the wind direction, there's the tail angle, and there's the wind direction relative to the turbine itself. And so there's quite a lot of different things you could be measuring. But if it's simply the tail angle, which in itself is quite interesting, that's quite simple to do with a potentiometer.
great. Yeah, actually I was thinking of measuring all 3 of them. So wind vane for wind direction, maybe a potentiometer for the tail angle, and then the yaw angle. That one could go 360 degrees, something like that. That's a little more tricky.
Well, in reality, if you're measuring the wind relative to the wind turbine rotor, it doesn't really need to be 360 degrees because it's unlikely to be coming from behind. It's realistically only going to move through less than 360 degrees. The wind is always going to be in front of the rotor or to one side, one particular side. But it's difficult to know where to site that wind vane because you can't put it in front of the rotor so easily. It's quite difficult to put it above or below, and if it's behind, it's going to be influenced by the rotor itself quite heavily. So that's the biggest challenge with that one, is where to put the put the vane. Unless of course you're looking at the yaw position relative to the tower, and there, yes, you would need something that would rotate like a wind vane through more than 360.
Yeah, I was thinking about it, but I need to think a little bit more maybe about this other option. Thank you.
Yeah. The
Strike recording your direction is incredibly useful for keeping tabs on the cable twist as well. It could be accumulating, and your data logger could almost send an alarm at 10 or 100 turns clockwise or something like that.
yeah, that's
Yeah, I agree.
that's
That's
a good
very
plan.
useful.
Yeah, good plan. The wind vane that I used in this project was actually reed switches which connected in and out resistors to give an eight levels of voltage. But yeah, there are definitely wind vanes which have a potentiometer full signal output. So cool. Okay, are there okay, great. Are there any more questions at all?
Yes, Matt. Can you hear me?
Yes, I can.
Nice to meet you. My name is Juan. We are talking from the National Park Administration in South America, Patagonia, Argentina.
Okay. Hi. Hi.
Hi. We have some questions. We have one equipment here, and we have a problem to set the time. We should set the time for recording, because when we get the data, we have the graphic lines are too small. So we want to ask you how we can set time to make it longer. So we have something like every 10 seconds, I think. The other question we have is how we can set the window, the winds measure. We don't know which unit on the table, and in that case, unit like in kilometers per hour or sections. Do you get to that?
Yes, I think I heard. It cut in and out a couple of times, but so there were two questions there. One of which is how do you set the sample time on this unit?
Yeah.
I think these are the questions. Now, that should be changeable by putting the unit into calibrate mode.
All right.
And then, do you have an FTDI, the USB to serial connector cable? Did John leave one of those with you?
Let me check because I'm the translator. I have the technicians
okay.
next to me.
Okay.
¿Tenemos el puerto que pidió? Sí. Sí. All right, we got it.
Okay. So if you put the unit into calibrate mode and then send the command S and then your sample time and then end with an E. So this is just a way I've got of uploading a new sample time. Then you should be able to change it to whatever sample time you want, where the number is in seconds.
Right.
It's written up in the Dataduino part of my website, so you might want to just read that before doing it. I'm just looking on my... I don't think I've included it. It should be on the instructions of the Dataduino.
All right. And in that case, we can check it later on the webpage, or we can go by mail. Maybe. I think it will be better.
Yeah, cool. And the other question I think was relating to the calibration factor for the wind speed. Is that correct?
Not the calibration. It's how to reprogram to get the data. I mean, sorry, I maybe will be more clear with that. We have a problem with the generation of the how you say that, the power. We have the shunt resistance. You know that? You get that?
Yes.
Have a constant of constant value of 5020.
Yes.
We want to know why we have that as a constant value. You know, the value, it's always the same. It doesn't change.
Okay. I think this is this one that's measuring the power consumption, so the current and the voltage?
All right.
I think it is. So it was Tom Dixon who's online as well, hopefully. I think that, I don't know if you've got any answers for that, Tom? Or is it not?
Well, none of the systems that I was helping John get installed involved current shunt monitors. It was all CT clamps, so I'm not 100% sure what we're talking about here. Perhaps you could explain what the current shunt is recording and what in the system. Is it the wind turbine's output?
Sorry, it doesn't hear very well.
Okay. Just wondering what the shunt resistance actually records. Does it record the current from the wind turbine?
Es la corriente del viento, ¿no? Es la constante. Lo que está midiendo.
¿Cuál? ¿Esta?
Lo que vos me estás preguntando es la constante.
¿Esto o esto?
No, él me está preguntando si lo que vos estás midiendo es la constante.
Estamos midiendo la velocidad del viento.
We are measuring the wind speed.
Estamos midiendo la corriente
We are measuring the power generated by the wind generator.
Estamos midiendo el voltaje de las baterías.
And we also are measuring the voltage of the batteries.
Y la corriente derivada a la resistencia.
And the power, the derivation power to the shock resistance.
Okay.
My language not the better. The best.
No, that's cool. This is, I think, a slightly more bespoke system, and I think I would need a bit more information on exactly what's been installed here. So maybe it's best we, because the systems that I supplied to John didn't measure any currents, and they didn't have any shunt resistors in them. So I'm not sure quite where the issue is.
Oh, I'm sorry, Matt. I think I know what he's talking about.
Okay.
When he says shunt resistance, I think he's talking about the dump load. So measuring
okay.
the current
The
going
current.
to the dump load.
Okay.
It's
Yes.
not an internal shunt resistance for measuring any current. And
Right.
actually, now that you say it, I think that the system installed in Bariloche, where these guys are coming from, it was made by Tom.
Yeah, I
think that's it.
I think it sounds like, okay, thank you, yes, that makes, yeah, I see. So it's the power to the dump load seems to be just at 5020 all the time?
Right.
Yes, okay.
Hi guys.
So there's,
yes. Sorry, I've arrived at the last minute because all of our internet has gone down at the university, so I'm sorry to have missed the entire thing, but it seems that I may have arrived at an opportune moment. I think I know the answer to the problem. The reason why it's measuring 502 all the time is because it's a bidirectional sensor. It's a Hall effect sensor that has a range of 10, 24, and when it's at 0, it measures should measure 512. So it also has an offset on it, which is the difference between 512 and 502, a 10 unit offset on it, and there probably is nothing going to the dump load at the moment, which is why it's measuring 502 and not moving. And the reason why it's 512, not 0, is because it has a measurement range from minus 150 amps up to 150 amps.
All right.
did you get that one?
Yeah, a part, because my technical language is not the best, but I think I got it. All right. Thank you. ¿Qué es esto? All right. It's. I don't have a good audio. Wait.
El valor que toma el data logger sobre el viento, por cuánto, si hay que multiplicarlo por cuánto, eso para contestar.
Sí, ahora por un segundo. All right, that's all for me, Matt. I appreciate your concern and your answers.
No problem. If you have any other questions, just email me. That's great. That's fine.
Okay, I think. Thank you.
Are there any other questions at all?
Not for me. ¿Tienes más?
¿Cuántos dígitos cada cuántos minutos debería memorizar?
We have one more question. If this possible. How do you think will be the ideal for recording the data in the data logger? About the time, every 10 seconds, minutes, hours.
So
why do you think the most useful?
I think the answer to this depends upon what you're trying to, what characteristics you're trying to see. So if you are looking at something like current or power to electrical devices, then you want to measure that in quite detail, so maybe every second measure that. But if you're looking at wind speed, you would like to measure it every second, but you only really need to record it every 10 minutes because and knowing any more data than that, it will just look, it won't help you that much. So it really depends on what you're trying to see.
All right, we got it. One more question, if you don't mind, and the rest of the people don't care.
Si el data logger se puede
We want to know if the
elaborar
data logger
datos
can save
de la
data
turbina eólica
from the turbine, could be the word. Sorry.
molino eólico.
¿Cómo se dice molino eólico en inglés? From the generator. Sorry? Sorry? Somebody speak just what?
Con paneles solares, si puede tomar los datos, el mismo data logger puede tomar
If
las dos
we want to know
generaciones
if you can use the data logger measuring the solar panel and the wind generator. You know what I mean?
Yes. I think that this data logger with the correct sensors could measure any of these parameters. So we could definitely measure power from a wind turbine and also power from a solar array. The only problem might be that we run out of inputs. So the unit that I've designed has 4 analog inputs. I think what the work that Tom Dixon has done, he has increased the number of inputs using what's called a multiplexer. So I think he has 8 analog inputs, and there could potentially be more. So we could definitely measure these different parameters, but it may need additional equipment than what you have already, I think.
Okay. Okay, thank you.
Matt, could I just add to that? It's the equipment installed at Fernando's office in Bariloche already has a spare current sensor on it. So actually the equipment that's there is already ready to measure a solar panel as well. It has a spare current sensor on it, and with the 8 inputs on the current shield that Tom has designed, at any point it can plug in a solar panel and measure that as if it were another wind turbine. There's really no difference on where the power is coming from. The only difference is the resource. You'd need a pyranometer in order to measure the solar resource.
Great.
Great.
Sorry, can I make a small comment? Hi, John. Rafael here from Argentina.
Hi, Rafael.
Yes. I don't know what the kind of sensors you have in Bariloche, but they're probably these 50 amps current sensors.
They're plus minus 150 amp LEM Hall effect sensors.
So my comment is that probably you would need a smaller sensor, the same line, the Allegro sensors, but there's a line of 20 amps and even 5 amps for probably the array is quite small. I don't know what current, but I don't know what voltage either, but probably the range will be too small for or the current range to measure would be probably too small for the 100 amp sensor. So
yeah, you're absolutely right. Well, it's a problem with these ones. They're very adaptable because you can use them on very big and very small systems, but in the small power generation systems they will lose resolution. But the advantage of these ones over the Allegro ones is you can loop the cable through, and each time you double the amount of loops, then you halve the amount of you halve the resolution, or you halve the range of the sensor. So 2 loops through the sensor would make it into a plus or minus 75 amp sensor, and then 4 loops through the sensor would make it into a plus or minus 33, 32 and a half, or 37 and a half, is it? My math is not very good, but I think you get the idea, right?
Yeah.
No, I thought they were the Allegro sensors. Those are the LEM sensors, right?
Yeah.
These are the LEM ones, yeah, which are quite. They have a big advantage over the Allegro ones in that you don't have to cut the cable, although most of the time we have ended up cutting the cable because we've had to loop it through a number of times in order to get a reasonable resolution.
Yeah, okay.
I've just in the chat window I've put a link to an article I wrote quite a long time ago now on DC current measurement, and it has some information about different sensors you can use, different methods you can use, invasive and non-invasive techniques, and brings in both the LEM and the Allegro sensors and some information about them. So maybe have a little look at that, might help.
Oh, great, thanks, Matt.
Yeah, thanks.
Thank you.
I've also put in the chat a blog post that I wrote just a couple of days ago that has some pictures from the install in Bariloche that we've been talking about here. So anyone that wants to see the equipment that's installed can have a look on there as well.
Great, thanks. Okay, I think, have we got any more questions?
La toma de datos.
Not for us in Patagonia, but we want to let you know that we can offer our data if you need it or if somebody needs it.
That would be brilliant. I'd love to see any data coming from these systems, certainly the ones that have been installed. So please just make a link via my email address, and that would be great to see some data, and I'll keep people informed. If anyone sends me their email address, then I can keep people informed of when I make changes or when things have changed on the projects. But yeah, I'd love to see any data at all coming from it. That'd be brilliant.
Oh, okay. You can count on that for us.
And just to let you know that this kind of theme of data loggers will be something that will be actively continued at the Wind Empowerment Conference. We have an entire working group dedicated to it, so the discussion will continue to develop, and any questions that people have, I hope we'll be able to kind of pass around in an email group beforehand, and then we'll be able to hear a lot more on this theme, because I think it's a really exciting, a really exciting project that we've got going here within Wind Empowerment. We're really lucky to have people such as Matt and Tom that are willing to design equipment like this for us. So thank you to both of them.
Cool, no worries. It's been a fun project. Maybe needs a few more iterations, and then we'll be at a great project.
All right, if there are no more questions, we'd like to thank Matt and then everyone that participated in this webinar.
Great, yeah.
Thanks, Matt.
All right, thanks a lot.
Thanks to everyone who came on. Brilliant. Cheers.
Cheers, and we really want to say thanks to you.